I officially started it, and then I will keep track of all what's going on. People are joining. Great. Okay, good afternoon, everybody. My name is Thomas Murillo. I represent Lehigh University, and we are producing the next lecture in the NERI Lehigh seminar series. Today's presentation is going to be titled Real-Time Hybrid Simulation, Developments, Implementation, and Applications. And our author today and our presenter is Dr. Oya Mirkan. She is the Associate Professor and Edward Hart Professor of Civil and Mineral Engineering at the University of Toronto. She received her PhD in Civil Engineering from Lehigh University in 2007. Dr. Mirkan was an assistant professor at the University of Alberta until 2010, until she moved to her current position at the University of Toronto. Dr. Mirkan's research interests are in developing and implementing real-time testing methods that couple computer simulation and physical testing with applications to the dynamic behavior of complex structures, vibration, mitigation, and structural control, modular steel structures, and wind loading under climate change. In addition to her research, Dr. Mirkan teaches several courses in mechanics, structural analysis, and dynamics at the undergraduate and graduate level. She is also the director of the newly established Center at the University of Toronto and at Climate Science for Engineering. So before we begin, I'm going to address about the question and answering. We're going to let Dr. Mirkan present the full presentation, and you may use the question and answering chat features in Zoom to ask your questions. If we would like, we could start a discussion by opening and allowing you to speak with microphone. But at this time, we would like everyone to please use the question and answer feature to ask questions during the presentation, and we will address them afterwards. So without further ado, Dr. Mirkan, you can proceed and share your screen and start.
Thank you very much, Tommy, for the introduction. Let me share my presentation. Can everyone see my presentation and hopefully hear me clearly?
We can hear you, yes. Looks good, and we can hear you.
Okay, thank you so much. So, hello everyone. As Tommy indicated, I received my graduate degrees from Lehigh University. I was very fortunate to work under Dr. Rickle's supervision on real-time hybrid simulation for my master's and PhD. Since then, I have focused on also different areas, including climate change, impact assessment, mitigation, and adaptation. but real-time hybrid simulation remained an active research area within my group, and this is what I'll talk to you about today. Before we start the presentation, if we take a quick look at recent literature, we can see that real-time hybrid simulation is a state-of-the-art testing method that is very versatile. If we look at the first study, they have implemented this testing method using a shake table. In the second study, the application included multi-axial loading instead of a single-axis loading. In the third study, we can see that the application of real-time hybrid simulation is extended to include distributed simulation, which means that the simulation is executed among multiple institutions. The fourth study here introduces wind-induced vibration mitigation. Commonly, in the earlier times, real-time hybrid simulation was used mainly for seismic applications, but this study introduced wind mitigation. And in the fifth one, we can see the application of real-time hybrid simulation to ocean structures that considers wave loading. And the sixth one is a recent study that uses a laminar box to do real-time hybrid simulation to investigate soil structure interaction. By no means this is a complete list, but we can see the active research area for both the implementation and the application of this testing method. Here is an example of a seismic predictive system. This is Torre Mayor office building in Mexico City. These large dampers during an earthquake will dissipate energy and mitigate the damage to the structural and non-structural components. Knowledge of structural performance from real-time tests of large-scale structures equipped with such devices is required for developing performance-based design codes to enable widespread use of such devices. And real-time hybrid simulation is an ideal test method to address this need. In 1960s, this testing method started as the dynamic test method, where we first idealized the test structure as a lumped parameter system. The inertial force and damping force characteristics are modeled numerically. The restoring force for pseudodynamic test is retrieved from the experiment. So if you are doing pseudodynamic testing of a 4-story structure, you need to build a 4-story frame in your lab. And the external load, which is on the right-hand side, is also numerically specified. So during the test, a direct step-by-step integration algorithm is used to solve the equation of motion to obtain the displacements, which are imposed on the test structure by hydraulic actuators. The load that is developed is measured by some sensors and fed back to the integration algorithm for the computation of next step displacements. So any uncertainty or complexity that is relevant to the restoring force vector is captured in the experiment. So this gives us a reliable testing method. When we extend it to hybrid simulation, the substructuring idea comes into the picture. And here you can see that the same 4-story structure is separated into 2 components. Part for which we have an experimental substructure to be physically tested in the lab is the experimental substructure, and part which is modeled in a computer is the analytical substructure. If you look at the left-hand side, we can see the implementation in the flowchart. The main difference is start right here after the integration algorithm computes the displacement vector. It is simultaneously imposed on the analytical substructure and experimental substructure. The restoring forces from both are then combined and fed back for the computation of next step displacement. So if we have components in our structure which are load rate dependent, in order to capture the accurate vibration characteristics of the structure, we need to perform real-time tests. So this is where real-time hybrid simulation comes into the picture. And in this block diagram, we can see that the implementation of RTS can be considered as two loops with where the inner loop has the controller, servo hydraulic system, and test structure. The outer loop has the integration algorithm and the analytical substructure. So inherently, both pseudodynamic test methods and hybrid simulation and real-time hybrid simulations, these are all they can experience accuracy and stability problems as a result of the error propagation. This can be from analytical substructure or from the experimental substructure. If you look at these types of errors, we can broadly categorize them as amplitude errors and time errors. Amplitude error can be overshoot, undershoot, and time error can be lead or lag. And when we study them separately, we can see that the time lag error is the critical one, which has an effect equivalent to decrease in damping, and it can eventually lead to instability. So if we go back and take a look at this block diagram, if we have tau 1 second of delay coming from our computational state determination analytical substructure, and if we have another delay of tau 2 seconds coming from the experimental substructure, for a combination of these two, we can destabilize the outer loop system dynamics. If we look at this delay-dependent stability analysis of the outer loop dynamics, we can model the delay as a constant delay tau term here. The measured restoring force has a delay tau, and the rest is the differential equation that we know from the outer loop dynamics. And we can cast this equation in state variable form in matrix vector format. In Laplace domain, if we look at the characteristic equation, we need to calculate this determinant. And the root of this characteristic equation is going to let us know whether our system is stable or not. So if the roots of the characteristic equation is on the left-hand plane, our system is stable. If it is right-hand plane, our system is unstable, which makes the imaginary axis the boundary of stability. When we have no delay, if tau is equal to 0, this determinant is a standard polynomial in S, whose roots we can easily establish and study. But the instant that we have a non-zero amount of tau delay in the system, the exponential term comes with technically infinitely many roots. So the earlier studies on this employed a linearization. So they introduced this approximation to represent the exponential term. And obviously, this would not be a valid approximation for large values of delay. Our pseudo delay technique employs something called recursive substitution, which gives us an exact relationship between the exponential term and this ratio of polynomials. And it can be shown that recursive substitution is exact on the imaginary axis when S equals I omega with this mapping condition. So with this recursive substitution, without any approximation or linearization, we can convert the characteristic equation into a standard polynomial in Q. We can study the roots of Q for stability, and when we find the T critical, which crosses the imaginary axis, we can then use the mapping condition to find the critical time delay that destabilizes the entire system. So we have published these delay-dependent stability analysis applied to single degree of freedom systems and multi-degree of freedom systems in these two papers. And then we focused on the tracking performance evaluation. So if we take a quick look at this plot where we see the measured displacement and command displacement on top of each other for a 30-second duration from one of our real-time Harvey simulation test results. At this scale, it is not possible to see the difference between these two signals. But if we take selected windows and look at them closely, we can see that in some instances there is lead between the measured and measured and command signals, and in some windows there is lag. So with that, we focus on establishing some indicators to quantify the tracking performance between the measured and command signals. So the very first indicators that we came up with rely on synchronization subspace plots, which is a plot where you put your measured displacement on the horizontal axis and command displacement on the vertical axis. If we look at the plot on the left-hand side, the purple line is the command, and the red marker represents overshoot error, and the green marker represents undershoot error. So on the left, we only have amplitude error. And when we look at the corresponding synchronization subspace plot, we can see that for perfect control, if the command was exactly equal to the measured, we would have a straight line with 45-degree inclination. And this inclination angle changes with undershoot and overshoot errors. Similarly, if we consider some toy signals where we have a command signal, lead and lag version, and if we look at this corresponding synchronization subspace plot, this time we see that with the lead and lag error, with the phase error, we no longer have straight lines in the synchronization subspace plot, but we have elliptical hysteresis that are clockwise and counterclockwise. So in the first set of tracking indicators, we use the inclination of the synchronization subspace plot and the area enclosed to come up with a measure for the error between the command and measured signals. But these were not able to completely uncouple the phase error and amplitude error. Then we improved it further. In this time, we still use synchronization subspace plots, but instead of calculating the area inside the synchronization subspace plot, we fit an ellipse to it using some image processing techniques that is typically used. And we also establish a relationship between amplitude error and phase error and the coefficients of the identified ellipse. And this gave us an accurate way of uncoupling the amplitude and phase errors. But the challenge with this particular improved tracking and amplitude indicators is that the image processing technique that is used to fit the ellipse so that we have these coefficients each time we fit an ellipse to the synchronization subspace plot, it requires the solution of a very large eigenvalue problem. So for that reason, this particular set of indicators were not it wasn't practical to try to use them as real-time indicators, so they didn't lend themselves for real-time implementation. They are still very useful for processing the results after the test when you don't have real-time conditions, but because of the high computational demands, these particular indicators were not implemented in real time. So with that, we looked at other ways of quantifying the phase error and amplitude error between the command and measured signals. And one way was to do this in frequency domain. And we came up with a new set of indicators that are able to uncouple the phase and amplitude errors, that are able to quantify them, and they are also computationally efficient so that we can implement them as online indicators. In fact, we use them within an adaptive control algorithm, which I will discuss in a moment. So at University of Toronto, we have implemented real-time Harvey simulation in two different platforms. The first one is it uses a Quanzer educational shake table. The hardware includes the shake table itself, and we need to have the sensors, the displacement and load sensors, as well as the relevant data acquisition platform. On the software side, the inner loop was already there. The Quanzer shake table comes with its own controller. What we needed to do was to introduce the outer loop with the integration algorithm. And we use Rincon real-time simulation coordinator to synchronize the two. And we published the development, implementation, and verification of this platform in 2015. Afterwards, we use this small platform to do a detailed analysis for tuned liquid damper structure interaction. Tuned liquid damper, as you might know, is a cost-efficient vibration control device, which is typically a rectangular tank placed on the roof degree of freedom of your structure. And if you want to do a dynamic experimental study for a tuned liquid damper structure interaction, you need to build a scaled down version of your structure as well as a scaled down version of your tank and do the test on a shake table. But in this hybrid platform, we were only using the TLD, the tuned liquid damper, as the experimental substructure, and we were modeling the rest in a computer, which enabled us to do a very detailed study where we were able to change the frequency ratio, mass ratio, damping ratio between the TLD and structure quite easily. Whereas if you needed to do this on a shake table, you have to build a separate structure to change each of these parameters. So we have we compared the accuracy of different TLD models. We did a detailed parametric study for structure interaction with TLD, and also we introduced some modification to the connection of the TLD to the structure by introducing this pivot and springs, such that when the structures move back and forth, the tank does not only move back and forth, but it tilts also. And this rotation engages more water quickly. And we investigated the efficiency of this type of connection between structure and the TLD using real-time hybrid simulation. The next platform I want to talk about is what we call a user reconfigurable platform. This time we used hydraulic actuators, and we have an NI-PXI system which has two real-time environments. One is the real-time PXI side, which is CPU-based real-time environment, and it also has a field programmable gate array, which is essentially a programmable chip. And in order to have communication between the actuator and this control platform, we have a data acquisition system that can handle LVDTs, load cell, and other sensors. So this was a significant undertaking. We had to start from scratch and separate all the tasks, including safe startup, emergency shutdown, command generation, either as predefined displacement force or using integration algorithm as it's required by real-time hybrid simulation. And we programmed some of these tasks on the CPU side of the NI-PXI platform, and we provided some of the tasks on the FPGA, and mostly the data acquisition, I/O, and the communication with the input-output modules, limit checks, data transfer, and data injection, and the control algorithm and was programmed on the FPGA. And we synchronized the two using FIFO or DMA approaches available in LabVIEW. So we have this user interface At the background, we used a technique called state machine, which is a programming technique in LabVIEW. So we separated the tasks into different states, and for each of these, we developed a LabVIEW code and we connect them together. And if we take a look at this distinction again, part of the implementation was on the LabVIEW side, and part of the implementation was on the Simulink side. So on the LabVIEW side, we had the host VI, which has the graphical user interface as well as the different states that I just quickly showed. And on the Simulink side, we have the model for the analytical substructure. And there is simulation interface toolkit where you can convert the Simulink model into an executable DLL and embed it in your LabVIEW model and run it from within LabVIEW. We have also encountered some challenges when we first put this system together, because National Instrument products are not made to control servo hydraulic actuators. So we kind of needed to customize our data acquisition systems with adapters. To name a few, we needed to introduce AC-DC converters or voltage to current converters. For example, in order to drive the servo valve, you need plus minus 40 milliamp control signal, but all you can issue from NI instruments is plus minus 10 volts. So we needed to get voltage to current converters, and all of these came with their own power supplies to energize the HSM solenoids and excite the sensors as well as these adapters. So this was part of the hardware challenge that we faced, but although we spent more than 2 years, 2.5 years to implement and verify this testing method, it gave us a quite transparent and flexible platform to come up with new applications and new algorithms and implement them and verify them experimentally. The first one that I want to talk about is the adaptive controller that we developed. So the idea is quite simple. This is the inner loop of real-time hybrid simulation. We have a constant coefficient controller. We have the actuator structure. And what we do in this particular case, we take the command displacement, we take the measured displacement. We have frequency-based online indicators which quantify the phase error and amplitude error between these two signals. We design a compensator to negate these effects, and we place that compensator in the forward path. And here is the LabVIEW implementation for this. So we have a PID plus structure, and in the second loop we have the adaptive controller plus PID and plus structure. So we take the command and measure signals, we take their FFTs, and then we extract the phase and amplitude errors. We use them to determine the coefficients of the compensator, and then we build the compensator transfer function that is going to place in the forward path that I just showed. So this way we can implement this adaptive controller quite easily in our user reconfigurable platform. And here, this video shows the comparison between a constant coefficient PID controller and the adaptive controller. In each case, we are tracking the same chirp signal, which is a sinusoid signal with increasing frequency. And the figure on top belongs to the constant coefficient PID controller. And here, the bottom, we are looking at the performance of the adaptive controller. We can see that as the input gets faster and faster as expected, the bandwidth of the system is exceeded, and we start introducing more delay between the more delay as well as amplitude error between the measured and command displacement, whereas the adaptive controller is able to make up for it. In this slide, I'm going to show you an improved version of this adaptive controller. So the main difference is that we are introducing a supplementary PID control to further remove the error. Because when we look at the details of this formulation, the frequency-based tracking indicators target the fundamental frequency of the signal, and it quantifies the error based on the fundamental dominant frequency. It works quite well when there is a dominant frequency in the command and measured signals. But if you have multiple frequency occurring simultaneously, the adaptive controller, as it originally implemented, starts to suffer. And this additional supplementary PID loop further removes that error. So the original version of the adaptive controller can be found in this paper, and the improved version, where we have the supplementary PID, it can be found in the second paper. We have also introduced a new state space formulation for the outer loop algorithm. So typically, we use integration algorithms that solve second-order differential equations simultaneously if we are talking about a multi-degree of freedom system. And what we have done here is we use state space formulation to recast the equation of motion in matrix vector form. This is the continuous version, and then we discretized it using different discretization techniques and different order holds, and developing some estimators to minimize the error, especially for nonlinear implementation. We came up with an efficient and accurate integration algorithm for the outer loop, and we published this study with experimental verification in 2016. And in this particular study, in addition to our National Instrument PXI system, we have also used a DSpace board to implement the integration algorithm, and we showed that it can be easily configured, and the state space-based integration algorithm can be implemented easily in different platforms. So with that, I can now talk a bit about some applications. Over the years, we have used real-time hybrid simulation to study different vibration mitigation devices. Some of them were passive devices. The first one here is called gyro mass damper. This device is based on one of my previous PhD students' work. It works very similar to tuned mass damper, but instead of introducing the physical mass, it takes advantage of a gear assembly. So inside this gyro mass damper, there is a set of simple and compound gears. The displacements, the translational displacements and accelerations that is introduced the device gets translated into rotation, and the free spinning last gear introduced the inertial force with very little mass, physical mass introduced. And in order to study the effectiveness of this new device, we performed real-time hybrid simulations for single degree of freedom analytical substructures, which represented the first mode of the structure. In the next two examples, we are again using tuned liquid dampers. The first one is a multiple tuned liquid damper, and to our knowledge, this is the largest tuned liquid damper that is tested together with a structure. In this particular study, we had 9-story, 12-story analytical substructures. So since we didn't need to build a scaled down model of the structure itself, we were able to test a quite large TLD and connect it with the model of the analytical substructure. And as you can see here, we have different cells. So theoretically, we can tune this TLD to first 5 modes or selected 5 modes of the structure. But to keep it symmetric, what we mainly studied was the first mode control with the middle tank. The middle tank was tuned to the first mode of the structure. The bigger side tanks were tuned to the second mode of the structure, and the back side tanks were tuned to the third mode of the structure. The third device here is an annular tuned liquid damper, which is specifically designed for wind tower vibration control. And we have done real-time hybrid simulations to understand the effectiveness of this annular TLD in reducing the response of wind tower turbines. The viscoelastic flux damper that is shown on the bottom left is a study in collaboration with Professor Christopoulos from University of Toronto. One of Professor Christopoulos's students developed a design methodology called P-spectra, and working together with them, we have performed single degree and multi-degree of freedom real-time hybrid simulations, around 200 real-time hybrid simulations to verify that design methodology. And these last two examples are active devices that we have considered. The first one is active screw jack device. This has the same idea as the gyro mass damper. It converts this time a rotational input. If you apply a rotation to the handle, the screw jack inside there is a worm gear is going to push or pull on the structure. So we automated this by introducing a DC motor and use this as an active component to understand the dynamic response interaction between this device and a structure. We performed real-time hybrid simulations. And the last one is an active mass damper, which is the study that I want to talk in a bit more detail. So in this one, and this study was a collaborative study with University of Waterloo with Professor Narasimha from University of Waterloo. We studied the development of a deployable autonomous control system. And this was the first use of robotics to enhance structural control. The idea is to provide temporary short-term vibration control for lightweight bridges. So if you have, if you know that there's going to be a marathon and the path also includes a lightweight bridge, in order to control the resulting vibrations, you can deploy one or multiple of these DAX systems, deployable autonomous control systems, and they will locate themselves on the proper location on the bridge. They will activate the control force and they'll try to reduce the vibrations. And the main advantages include the fact that you don't need to introduce a permanent installation. You can remove these devices from your structure after the event ends, and you can use the same device in different bridges. So the DAX prototype has these components. It has the unmanned ground vehicle, which is a Husky from ClearPath Robotics. On top of it, there is an electromagnetic mass damper. This is an active mass damper. The UGV has vision sensors in the front and back, and there is onboard onboard computational platform. This time we again use National Instrument products, but instead of a PXI system, we used a compact Rio. So with this application in mind, we can look at the overall system. So we have the lightweight bridge, and it is going to experience vibration due to the pedestrian loading, and we are able to employ one of our DAX devices. So what will happen is in a real application is first the DAX will detect the vibration. It will determine the optimum location that it should go. It will go there on its own because it is an autonomous system using its vision sensors. And then it will activate the EMD, the active mass damper on top, to generate the required control force. And this way, it will mitigate the vibration. So to do the hybrid simulation, we have to consider a few aspects that are different than the regular application of real-time hybrid simulation to lumped building structures where the control devices as well as the loading are stationary. So the hybrid simulation has the same idea. We have to use substructuring. In this case, we use the bridge as the analytical substructure, and we have the DAX system as the experimental substructure, and the shear type load cells will capture the load, which we will exchange between the analytical and experimental substructures. There are a few challenges that are different than previous real-time hybrid simulation applications. First of all, this is an active device, so our controller needs to also compute the optimum control force, and it should introduce it to the EMD so that we can introduce the control force at the bridge, at the load cells. So that is a fact that comes with the active nature of this control device. But if we consider the hybrid simulation aspect, there are challenges associated with modeling the structure as well as the loading. So in wind application on building structures, or in earthquake application on building structures, your loads are forces that are defined at the floor levels. The external loads don't move, as well as the control device. So even if you have an active control device, such as an active tendon, the location of it is fixed. In this particular problem, both the loading is moving as well as the control device. So in order to address these, we have recast the dynamic problem in modal domain using state space, and we were able to introduce the mobility of both the load and control device accurately in the formulation. So this required an original formulation of the real-time hybrid simulation problem. And we also needed to be aware of the interaction between the DAX, the control device, and the structure, which changes the effectiveness of the desired force. So we studied several different configurations with different QG designs. And this paper also was published in 2019 that summarizes this novel application of real-time hybrid simulation. So with that, I want to finish my presentation. I want to thank all the different collaborators, the sponsors, and last but not least, all the different graduate students and postdocs who over the years worked on the research that I just presented. So I would be very happy to take the questions if you have any. Thank you for your attention.
Thank you, Oya. That was very exciting, especially from my point of view, with my research in real-time hybrid simulation at Lehigh University. It's interesting. Like 17 years ago, just a personal note, 17 years ago is when I first started at Lehigh, and you were a graduate student working for Dr. Rickles, and we were working together to both, come to the same point 17 years ago, and what we're doing with our research. So it's amazing to see. I have actually, if I could start, I will go through the questions right now. We have one. I would please ask that you do put your questions in the chat, or if you don't want to chat, just say, I would like to, talk live. That would be okay. My first question really is just a two-part with compensation. We have experience with compensation as well here. And I wanted your feedback on being able to predict, or how are you looking at initial parameters for compensators depending on types of tests, or knowing that if you're going to do a test that is, fairly sensitive, that you don't want to damage it on the first try. What are your applications or methods for prediction of these coefficients for the compensation methods?
Thank you, Tommy. That's a very good question. The controllers that I have introduced, I think I'm showing the slide for the very first version of the adaptive controller. We have a traditional PID controller sitting here. So this compensator is not responsible for the whole tracking. It is just there to fine tune it. So and since it is in the feed-forward path, technically, if this compensator is stable, and if you have a stable loop, technically you cannot destabilize the system. So that is also one aspect that we considered. Anytime you put something inside the control loop, you may destabilize the system. So with that, we already have a stable and acceptable tracking performance from a constant coefficient controller, such as a PID controller. And this compensator starts acting as it develops the signal, because I didn't have a chance to go into the details, but in order to implement this, you have to have a moving window. And the first time you start actually taking an action is at least you should have half a period long signal. Once you have that, you can accurately calculate the errors and design your compensator. So with that, the risk of damaging the structure until it converges is not as significant as other cases where you need to really find the right parameters from the start of the test.
Okay, no, thank you. I appreciate that. And then just to follow up quickly, and I know we have a couple more questions. When you showed with this adaptive control, you introduced another, we'll call it term, in that being a PID loop. What's the advantage of adding a PID loop, and how are you going about tuning that instead of like saying adding another, like a fourth term to the existing adaptive control?
So this one, as I tried to explain in the presentation, we realized that for some cases where there are multiple dominant modes, because of the formulation that we have introduced in the adaptive component, the performance starts to suffer because we are only using one dominant frequency. So we had different options. If there is in the literature, there are other frequency-based indicators which are using an averaging of multiple frequencies, but still that averaging introduces some error that eventually contributes to the performance degradation. So this PID loop is secondary PID loop. We still have another main PID that is sitting here, and to tune the parameters of this PID, again, since we are out of the feedback loop here, from stability point of view, we are a bit safe, but still the coefficients require some tuning at the beginning of the test, just to be able to come up with the right set of parameters. And when we are doing, we have also, we used to do that at LEHIGH too. We have a virtual real-time hybrid simulator where we model the servo-hydraulic system in detail, so that we can have a good estimate even before we start the test, and then fine-tune it during the actual test until we observe the best agreement between the target and measured displacements.
Okay, great. Thank you. I appreciate that. I'm going to go through the questions. We have a few now. I'll go in chronological order. First in the chat from Hytham. Is it possible to do real-time hybrid simulation if the analytical substructure and the experimental substructure have different timescales? An example, 1 second in an experiment, 14 second and an analytical. So we're looking at different time domains.
There are ways to synchronize them, right? But the slowest one would govern. The question is, if you can actually, but if you have fast enough analytical substructure state determination and fast acting servo-hydraulic system, but they are not using the exact same time interval, when you are synchronizing the two, you can add an intermediate component which synchronizes the two. So the synchronization is quite manageable in different platforms. We have done it in DSpace also, and as well as the NI platform. That is possible. But what might be an issue is that if you have a very complicated analytical substructure to converge, it requires a long time. Then that would determine how fast you can go, and then the resulting test most likely won't be real time.
Next question from Camilla is, in the example of the TLD on the educational shake table, did you encounter any distortion or scaling related issues?
In terms of the investigations that we have done, these are like this scale of TLD is even larger than most of the TLD studies that used a shake table where they have the TLD on top of a structure. So the comparisons are done among each other. We didn't go back and compared it to a real life structure, but the scaling could be done. So it didn't have any impact on the scale effects. And you can find a lot of other studies that use even smaller TLDs on shake tables, where they also have a 3-story frame, which they put on the shake table together with the TLD.
Great, thanks. We'll go back to the next one from Brian. How did you incorporate a complicated computational driver like a nonlinear structural analysis in LabVIEW? And my guess is the Simulink toolbox. That's my guess.
We can do it in Simulink toolbox, but there is still limitations. Right now, that is the topic of one of my PhD students right now. He is developing a finite element based library for specifically for FPGA application, but we have not yet finished the study. So we are working on it so that we can have nonlinearity introduced into hybrid simulation in a realistic manner. So far, as Tommy indicated, the way that we are currently doing is with a DLL, which is converting a Simulink model to an executable file to be executed on LabVIEW. And we can model the nonlinearity there also. But in order to make it a bit more efficient, we are right now looking at some parallel computing techniques to implement a simplified version of a finite element analysis on the FPGA itself.
Oh, that's great. I was actually, I'm personally very interested in seeing the progress with that with the FPGA, so I'll probably discuss that with you as well offline. I'm going to go to the next one from Diego. Is thinking about obtaining more realistic answers, it would be ideal to combine a finite element software, MATLAB Simulink. Is it possible to do this, or is it possible to work with more complex and nonlinear analytical substructures as it currently? So kind of like blends in with the previous question. Yeah. If you want to add anything else to that.
Currently, this LabVIEW NI platform cannot do it, but there are, for example, just in 2020, I think, let me try to remember the university, Nevada, I think, Nevada Reno. They published 2 papers where they have used OpenSeas with OpenFresco, with MTS flex test software. They are not. It is different in the sense that in our platform we are responsible from every single aspect of the real-time hybrid simulation. But you can have other platforms where you have different ways of combining the analytical substructure with experimental substructure, and they have done quite sophisticated nonlinear real-time hybrid simulations. And what they have also concluded is that the one interesting conclusion was the selection of integration algorithm depends on the nonlinearity of the analytical substructure. Several integration algorithms that are typically used, especially explicit ones, did not perform very well when the numerical substructure was highly nonlinear using OpenSeas. So I don't remember the name off the top of my head, but there are some recent studies that do introduce realistic nonlinearities and which also uncovers further issues that we need to take a closer look from within real-time hybrid simulation also.
Right. Yeah, I'm actually very familiar with what MTS is doing in hybrid simulation, et cetera, what you had talked about. I posted a link in the chat if anybody is interested. There's a YouTube video that MTS provided on hybrid simulation and everything you just discussed. So if you want more information, look at that link. All right, so we'll go to the next question from Eric is, what is the bridge scale limitation on the current vehicle?
Bridge scale limitation. So this can be used for a footbridge that should be lightweight, and what we considered were either wood or aluminum wood bridge. And if it is if you are only going to use one of these devices, that is that would be the structure that you should consider. But if you have a bit more weight on the bridge itself, which is no longer considered lightweight, you may consider deploying multiple of these devices. So with a single device, I would go with an aluminum or wood lightweight bridge, but you can also employ multiple of these devices to increase the control force.
Okay, great, thank you. I'm going to next question is based on the compensator techniques again. Is there a range of total time delay that is satisfactory for the compensators?
So if I restate the question, Is the question asking the final, like how after we introduce this compensator, what is the resulting time delay range, or what is the time delay range and that should exist in the PID standalone feedback constant coefficient controller for this additional adaptive compensator to be working?
So we'll ask the participant. It's anonymous, so I'll ask the participant if they want to ask again to rephrase the question. But we'll move on to the next question, and we'll come back to that. Is overall, what were the biggest from Alejandro? What were the biggest challenges for creating real-time target systems? For example, for the shake tables or the hydraulic actuator.
So it is, as I said, it depends on how you are designing your architecture. So in this platform, we chose to have a fully transparent system. So we have spent the time to implement all the actuator control components in our LabVIEW code on the PXI side or on the FPGA side. But if you are going to the route where you are going to use a turnkey controller that comes with your actuator or shake table, for example, in the smaller educational scale, in this one, we relied on the existing controller. So we didn't need to spend the time to implement this controller. It was already there. We just took the task of introducing the outer loop and synchronizing the two. And we also introduced a velocity feed forward to fine tune the controller so that it tracks the command displacements better. And you can, although this was a small scale application, you can scale it up as Tommy has provided the additional information. Typically, for example, for MTS systems, the controller comes with the actuator, and even if you can afford to get the real-time hardware simulator, you may have already a platform to use, and you can just introduce your analytical substructure and use it. But if you are developing it, the controller is quite challenging for the servo hydraulic system, as typically also the control platforms are not typically used for servo hydraulic system control, so you need to also handle some hardware challenges.
Great. We'll take two more questions because I know we're about at the end. We're at the end of the presentation. So the seminar, from Ali is, did your team perform any uncertainty analysis by considering uncertain structural or loading parameters, especially in analytical or numerical substructures?
I'm aware of such studies, but we didn't go there.
Okay, and then we'll take our last question from Carol, is from Polytechnic Montreal and former University of Alberta graduate. Two general questions we'll go through. One, how to resolve the feedback instabilities when an experimental substructure has more than 3 degrees of freedom. We find it very challenging to control many actuators using MTS controller and return a stable force feedback to the numerical models using OpenCs.
Yeah, that is a very platform-specific question. And at LEHIGH, when I was there, we had a pulsar system, and the actuators were also not MTS actuators. So I only worked in such a platform at LEHIGH. And when I moved to Canada, and this is the platform that we have developed and worked with. So I'm not sure if I can easily answer that question without looking into the details of the platform itself.
Right. I mean, in my experience, I could maybe give a little bit, is the number one thing is synchronization of your signals. So time delays are very important. Sometimes you need to extrapolate feedbacks so that they align properly. So you want to make sure that you're using a sample rate that's very small so that you don't create any numerical errors. And then also, two other things are your solver. I mean, what kind of explicit or implicit algorithm are you using? Typically, explicit algorithms might be better. And then, finally, you could even look at damping of the overall model. Sometimes increasing numerical damping will produce a more stable system. So again, from my personal experience, I hope that helps. And then the last question would be from that same person, Kamal, is in friction, for example, forces generated by the friction in the actuator when you've have 8 actuators or so. Anything, how do you look at that? Any suggestions based on friction in the actuator?
Friction.
Yeah.
Okay, so
I guess that's more of like a hardware specific thing. I don't know if this is really applicable to you. I mean, for Kamal, I would say maybe if you want to discuss that offline with us, myself and Oya, we could discuss that in more detail.
Definitely.
Okay. All right. I think that's it, Dr. McCann. Thank you so much for your time. We really appreciate this. And, we look forward to more research from you. Hope to have you on again when you have more things to share with us, and hope everything is going well for you during this time.
Thank you, Tommy. And it was really a pleasure to be back at LEHIGH, even it is virtual.
Exactly.
And I hope that we can get chances also with the participants to meet in person soon.
Absolutely. And final note is that this webinar will be archived through the Design Safe website at the LEHIGH portion. So if you are looking for that, please visit our site. In the next couple of days, it'll be available. And if anybody ever has any questions, please reach out to myself or Dr. Merchan, and we'll be glad to help you. So today, that'll conclude our seminar for today. Thank you for joining, and hope to see you guys soon.